Moving into this new chapter, chapter 5, we're going to start by exploring area under a curve, distance, and this new concept called a Riemann sum. So this is a little intro section, the first section, 5.1, and it's going to lead us right into 5.2, where we're going to talk extensively about this idea of what's called a Riemann sum. But to start off with, to sort of motivate where we're coming from and what we want to do, let's consider this idea of the area under a curve. Like if we wanted to actually find the area under a curve, how could we do that? And rely a little bit on what we know about geometry. So let's take a look at, and I just grabbed this image because I liked it, and I have a nice little Desmos app that we're going to go over and look at with this particular curve. It's a sine function that's been added to a linear function to give us kind of this squiggly up and down. So let's say we have a function, doesn't matter, it could be any function. Let's say we had a function y equals f of x, and let's suppose that we want to actually find the area under that curve. So we want to find this area. We want to find the area, and I just, it could be, in any region we're going to say from A to B generically here in just a second. But on this curve, let's go from 0 to 6. These lines that I've put on the curve. If we wanted to find that area, so how could we do that? So if we wanted to find the area under some curve, in this case y equals f of x, from x equals 0 to x equals 6. It could be anything. This specific curve, those are the numbers that I've picked. But if we want to find the area under a curve from one x value to another, and when I say under a curve, I mean under the curve to the x-axis in this case. So we are looking, for this visual, we are looking at a function, a positive function. Y equals f of x is a positive function. So how could I find that area? Well, there are a few things that we could do. We could estimate the area. That is where we're going to start. We could estimate the area, break it up into something that we do know how to find the area of, because we don't know how to find the area under a curve. This is not a geometric shape that we know how to find the area of. So what we could do is we could say, okay, we don't know how to find the area of this curved area bounded by this curve, but what we could do is we could break it up into something that we do know how to find the area of. For instance, we know how to find the area of rectangles. We know how to find the area of triangles. We know how to find the area of trapezoids. So there are geometric shapes that we know how to find the area of, and we're going to pull from those. So we're going to pull from what we know, and we're going to say, well, I could use rectangles to approximate it. If I used a single rectangle to approximate it, I have to decide what the height is. So maybe I use this being 6 over here. This would be the right-hand endpoint. This length from here to here is 6 units. And I need to find out, that would be the width of my rectangle. I'm going to use red here so it's clear. I need to find that, and I'm going to even make that a little bit thicker. So I could say, okay, let's use this height right here and create a rectangle that has width of 6 and height of whatever that height is. So we could use one rectangle. Now, would that be a very good estimate? No, nope, that's not a very good estimate of that area. It is an estimate of the area, it's just not a very good one. So how would we make it better? Well, we could say, well, instead of just a single rectangle, what if I used 2 rectangles? So instead of saying let's go the entire width, what if I split this up and I said let's make 2 rectangles to approximate this area, and then I use those rectangles to approximate that original area. Now we're better than when we used just one rectangle. Now the width, by the way, of my rectangles is 3. The width is 3. Both of them have the same width. They're both a width of 3. Their height is being determined by the function, and I am using what's called the right-hand endpoint of each interval to determine the height. So this point right here, I'm using that as my height to draw my rectangle, and that is f of 6. And then this one, because this is 3, that height that I'm using is f of 3. We don't have to use the right-hand endpoint. We could just as easily have drawn our rectangles from the left-hand endpoint or the midpoint we could have used to find the height, and we'll explore all those different options when we get into this in a little more detail. But what if we said, okay, so this is still not a great approximation. What if we used, instead of just 2 rectangles, what if we used 4 rectangles, right? Like the more rectangles we use, the better an approximation this is going to be. So what if I use, let's jump all the way up to 6. What if I use 6 rectangles? So to use 6 rectangles, I would draw in one here. I draw one in here. Now I maybe don't need this as thick. I would draw in a rectangle right here and here and here. 6, by the way, that orange line is a little off of 6. 6 is right on my grid. And so notice that when I use more rectangles, that this area, that's still an approximation clearly of the area under the curve. It's not the exact area under the curve, but it's getting better, certainly better. 6 is certainly giving me a better area under my curve than 1 rectangle did. 6 rectangles is better than 1. And what would be better than 6? Well, 12 would be better than 6. Or 100 would be better. Or 1,000. Or even 1,000,000. Or how about we let the number of rectangles go to infinity? Because now we are in calculus and we can do that because we can take limits. So what if we made the number of rectangles that I'm using to approximate the area go to infinity? What's going to happen is we are going to get the exact area under my curve. And we can do all of that. We can come up with an expression to represent the areas of these rectangles. We can let the number of these rectangles go to infinity, and we can use everything we've built up so far in this class with our limits and knowledge of how to evaluate limits. We can actually figure out what that area is, not just an approximation, but what the exact area under a curve is. So I want to show you guys a nice little, I've done this by hand here on this video so far, but I want to show you a nice little representation of those rectangles approximating the area in Desmos. So I'm going to pause and we'll head over to Desmos and take a look. Here is that same exact curve that we were looking at. It is actually minus sine of x plus 0.2x plus 1. That is what f of x represents here. We could look at any curve we want. We could change the curve. We'll use this applet to even change the curve. But what if I wanted the area from 0 to 6. So if you can look on the screen here on the x-axis, you can see a little purple line from 0 to 6. So what if I wanted the area from 0 to 6 under this curve to the x-axis? So you can visualize that being filled in. If I wanted that area, I could approximate it with, just like we did on the earlier portion of this video, I could approximate it with 1 rectangle. Right? And notice here the rectangle is being built. The width of it is the entire interval since there's only one of them, so from 0 to 6. And the height, I'm using the actual height of the function at the what's called the right-hand endpoint of that interval. So at 6, I went up, found the height of the function, and I used that as the height of my rectangle. So here is 1 rectangle. Not a great approximation, right? 2 would be better. 3 would be even better than that. And notice each time I'm going up with the number of rectangles, what's happening is the width of each rectangle, as the number goes up, the width of the rectangle gets a little smaller, and then the height is still being calculated using the right-hand endpoint. So from 0 to 2, the height of that rectangle is being determined by the value of the function at 2, what's called the right-hand endpoint of that interval. And then for the interval from 2 to 4, that rectangle has a width obviously of 2, and the height is being calculated by using the height of the function at the right-hand endpoint, which is 4. And then 6 is being used. And we could say, well, what would be better than 3? Because that's still, that's still clearly an approximation. What makes it better? We could go up to 4 rectangles, or 5 rectangles, or 6. We could go up, 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 up. This particular applet you see right there as we're going up, how those, now we're up to 25, and that is actually the limit of this visual that I have for you, that we can go up to, only go up to 25 on this. But what you can see right here is once we get to 25, it's still an estimate, right? Some of those rectangles are overestimates and some are underestimates, depending on if the function's increasing or decreasing. But when you add them all up, you get an approximation that gets closer and closer to the actual area under the curve as the number of those rectangles increases. And in fact, we can let that number increase all the way to what we think of as infinity, right? Like it doesn't ever reach infinity, but we can let the number of rectangles approach infinity, grow without bound until we have an exact area under the curve. Okay, so we can actually find the area under the curve by using our estimation techniques along with calculus and our limiting knowledge. Okay, so I actually, sorry, I stopped that at 23. We could actually get it all the way up to 25. There we go. There's 25 rectangles under that curve. Okay, so for our first example of actually computing areas under curves, so we have the general idea. The idea is that we're going to use shapes that we know for finding area, and we're going to make estimations. And then we're going to let the number of, in this case, rectangles go to infinity to give us the exact area. Now that part comes actually in the next section. So this section, we're really just going to practice this general idea of how do we create these mathematical expressions that will estimate the areas for me. And then we'll get into how do we then calculate those areas in the next section. So let's take y equals x cubed, f of x equals x cubed. Let's look at it from 0 to 1. And let's find the area under that curve. So I drew y equals x cubed over here. And the area that we're looking for is this area. So here is 1. And here is 0, and that is very wide, so let me make that a little bit thinner. There we go. Maybe that's a little too thin. And we want this area under here. So let's estimate that area. Now, we are told to estimate it using 4 rectangles. So we're going to start by using 4 rectangles, and this idea of right-hand endpoints. So what that means when I read that is that I have an interval from 0 to 1. I'm going to divide it up into fourths. And so from 0 to 1, if I'm dividing it up into 4 intervals, then what that does is that makes the width of each of those, we call it actually delta x. Delta x is going to be the width of each interval. So in our case, the width of the interval is 1 minus 0 divided by 4. So the width of each interval is 1/4. Okay? Generically, we'll write this up, but generically, delta x is going to be b minus a over n. Okay? The width of the interval divided by the number of divisions. Okay? So that's what we're going to do. Each of these is 1/4, so if we go from 0 to 1, obviously this is 1/4, 1/2, 3/4, and then 1. So we're going to divide it up into 4 rectangles, and it says use the right-hand endpoints. Right-hand endpoints means when I go to build my rectangles, I want to use the right-hand endpoints to create the heights. That red line is really wide, so I'm going to make that a little bit less wide on the screen. And I'm also going to go ahead and put in the same endpoints that we had when we divided up the interval on the other screen. So we're going to come in here, we're going to create 4 rectangles using the right-hand endpoint. So the first interval is from 0 to 1/4. So I go to the right side of that, which is 1/4, and I create a rectangle. And then 1/4 to 1/2, I'm going to go to the right-hand side of that interval, which is 1/2, and I use that to create my height. And then I go to 1/2 to 3/4. I go to the 3/4, use that right-hand point, 3/4, use that function value to create my height, go to 1, use that function value to create my height. And then that is going to be, I'm going to look at the area of each of those. I'm not going to scribble through them, but I'm going to look at the area of each of those rectangles to give me an estimate. So the estimate, the area, is approximately, right? I mean, the area under the curve is approximately going to be equal to the area of each of those rectangles. Well, how do we find the area of a rectangle? Well, it's the width times the height. Well, the width of each of these, remember, delta x is the width of each interval, which is actually the width of the rectangle. That's how we're building these rectangles. And we showed on the other screen that delta x was 1/4. And just, I'll put a little reminder here, that was 1 minus 0 divided by 4. So it was the length of the interval divided by the number of divisions, which we had 4 divisions. We were told to use 4 rectangles here. So the area is actually going to be, each of these is 1/4. or delta x. And then the height of each one depends on the function value. So our function is x cubed, but I'm going to write it this way to start off with. So it's going to be f of 1/4 times 1/4 plus f of 1/2 times 1/4. Notice that this is our height times our width. Height times our width. Each of these areas that I'm calculating here is simply a height times a width. It's just the area of a rectangle. Rectangles are simple shapes to compute areas of. It's why we use them. Let's get this all on the screen. Plus f of 3/4 times 1/4 plus f of 1 times 1/4. And that gives me my 4 rectangles. 1, 2, 3, 4. We've got 4 rectangles here. Those are the height of those 4 rectangles. And we could then go in and actually compute the areas. I notice here, you know what's kind of nice here, is that 1/4 is consistent in all of them. So you could factor it out and then compute them. I'm going to go ahead and speed up the video and just plug in these numbers here, and we'll see the final calculation, because now it's just plug and chug. This is 1/4 cubed times 1/4 plus 1/2 cubed times 1/4. So what we have found here, and I just did those calculations, sped up the video a little bit so you could see those, didn't have to watch the actual mechanics of plugging those into a calculator and computing those. But we ended up with an area that is approximately 25/64, or if you want to put it in its decimal approximation, 0.39. Now, I want to be really clear. This is a definite approximation of the area under the curve, y equals x cubed. You can see right there, the rectangles we've drawn, we can see that those rectangles are actually going to give us an over. You know, if we were asked, is this an over approximation or an under approximation? Well, every single one of those rectangles is giving us more area than what was actually under the curve, right? If we look at the curve here, I'll draw the black area under the curve, and you can see that those rectangles are clearly giving us a over estimate, right? This is more area than is actually under the curve because the rectangles are giving me more area than what is actually contained by just the curve. Okay, so that was an overestimate. So we can also compute these using the left-hand estimates, and then we could think about if the left-hand endpoints, then we could think about if the left-hand endpoints give us an over or under estimation. So we'll do that in just a second. I wanted to just mention, you know, this is a lot of words, and we have a way to express this this question using 4 rectangles, use 4 rectangles and their right-hand endpoints. We have a way to express that, and we write it like this, like R sub 4. When we're talking about finding areas, if I use R sub 4, that means exactly this. Use 4 rectangles, and R says use the right-hand endpoints. So again, I will summarize that after we finish this example, but I wanted to mention that there is a way to write that. Rather than always writing out, use 4 rectangles and the left-hand endpoints. We could say R sub 4, and we would know that's exactly what it means. So in a similar way, here, use 4 rectangles and the left-hand endpoints. So again, if we want to use 4 rectangles and we want to use left-hand endpoints, so we're going to do a very similar calculation, except we're going to build our rectangles a little bit differently. This also has a notation. If we want to use left-hand endpoints and 4 rectangles, we say L sub 4, and that means use left-hand endpoints, and the 4 tells us use 4 rectangles. Okay, so we're going to go back to the graph and we're going to redraw our rectangles for the left-hand endpoints here in just a second, but to be clear, we would do the same exact thing that we did before. We'd say, okay, so we want 4 rectangles. We're going from 0 to 1. If we want to divide that up into 4 intervals to build rectangles on, I have to take the length of that, right? I need to build 4 rectangles, so I need to take the length of that. My delta x, notice, is going to be the same because we're using still 4 as our divisor. But if we want to find the width of each interval, we're simply going to take the length of the interval, which is from b minus a. That's b minus a. We went from 0 to 1, so we go from 1 minus 0. And we divide by 4 because we want 4 intervals. And that gives us a width of 1/4 for each of them. So then I can come back up here and say, okay, so it's got to be 1/4, 1/2, 3/4. Those have to be my divisors where I'm going to break up the interval that I'm looking at, and I'm going to build my rectangles on top of those widths, which are going to all be of 1/4. So let's go ahead and come back here. Here we drew the rectangles in red. We drew the right-hand endpoints, and it was an overestimate. And you know what I'm going to do right here? I'm going to say the area is, I'm going to add a little notation in here because now we're going to do a second area estimate. So the area here that we're looking at approximated with R sub 4. Remember that that means 4 rectangles with the right-hand endpoints. So this was right endpoints. We did that in red. So I'm going to go ahead and switch the color, and let's do blue, and let's do the left-hand endpoints in blue. So we're going to have the same graph, but now when we draw, let's zoom in a little bit. Now when we draw the rectangles, we're going to actually use the left-hand endpoints to find their heights. So notice that the left-hand endpoint on the first interval is 0. So I am drawing, I know it's kind of hard to see because it's super small, but it has no height. It's not actually a rectangle, it's just a line. Notice that my height of my first rectangle is 0. So when I draw my rectangle, it doesn't have any height to it. So it's literally just a line right there. And I'm going to zoom back out so we can draw the rest of them. Now on the next interval from 1/4 to 1/2, I use 1/4 to give me my height, and then I draw the rectangle across. Let's make that a little bit thicker here so we can see these. And that gives me that rectangle, and then from 1/2 to 3/4, I use the left-hand endpoint, which is 1/2, to give me my height, and then I draw it across to give me my rectangle, and then I use 3/4, draw it across to give me my rectangle. And this area would be the area, I can approximate the area using left-hand endpoints. Now, we're going to do this here in just a second, but quickly, let me just ask this question. What do you think? Is this going to give me an overestimate or an underestimate of the actual area under x cubed? Pause on the video and hopefully you immediately said underestimate, because each of those rectangles, notice, is actually under the curve. It's based on the way the curve is increasing for this particular example, but each of those rectangles is actually under the curve. So when I calculate the area and add up all of those 4 rectangles, it's going to give me a smaller area than is actually contained by the area under the curve. So just keep that in mind. So let's go ahead and do left-hand endpoints. I'm going to zoom out here so we have some space underneath. And now let's approximate the area. So another area approximation would be to use those left-hand endpoints. So I would take f of 0. So again, remember, we have to add up 4 rectangles, right? Just like before. So the first rectangle is f of 0 times 1/4, the width. So it's the height times the width. F of 1/4 times 1/4. F of 1/2 times 1/4, and f of 3/4 times 1/4. And I'm going to go ahead and I'm going to calculate all of those. I'll speed up the video so you don't have to watch all the calculations, and we'll come up with an estimate using the left-hand endpoints. Okay, so now we've calculated the area using the left-hand endpoints. And the left-hand endpoints have given me an area of approximately an area of 9/64 or 0.14. Now remember, this was using the left-hand endpoints. The left-hand endpoints of each of the intervals. And we can look up on the graph and we can see clearly that that is giving us an underestimate of the actual area. Underestimate of the area. That's a definite underestimate of the area. We have a lot drawn on the graph right now, but if you can visualize that let's make it a little bit wider here. You can see that curve right there. There's our function. And you can visualize, if you looked at the area under just that curve to the x-axis, it is clear that there is more area under that black curve than there is in those 4 blue rectangles. So that's definitely an underestimate. So we're looking at an underestimate right there when we use the left-hand endpoints. Now, that is not always true. It totally depends on the curve. That's because this particular curve was increasing. So when we use the left-hand endpoints, we were creating rectangles that were all under the curve. And when we use the right-hand endpoints, they were all rectangles that were over the curve. Now, a curve that both increases and decreases, if we could go back and look at that other function we looked at the beginning where it went, it had a curve that looked like this. Then when you're drawing your left-hand endpoints, if you're drawing left-hand endpoints, notice this curve here is both increasing and decreasing. And so notice some of the rectangles are under and some of the rectangles are over. So do not just make an assumption that right-hand endpoints are always overestimates and left-hand endpoints are always underestimates. That is not true. That just depends on what the curve is. It just happens in this case we had an increasing curve. So that was the way it worked out for this particular case. Now, we can see right now what we've created is some bounds for the estimate of the area, right? We know our area under x cubed from 0 to 1 is somewhere between 9 over 64 and 25 over 64. If we wanted to make that estimate better, guess what we could do? Instead of using 4 rectangles, we could use 8 rectangles. And that would give us even better bounds for the right and the left hand estimates. Then we could go even further. We could do 16, 32, we could do 100, we could do 1,000, we could do a million. We could let that number of rectangles go to infinity and it would give us the exact area under this curve. Okay, so that's where we're headed. This is giving us an idea of how we're going to do it. I want to do one more piece on here before I end this video. I want to look at a way to just express this sum of the, right-hand endpoints. So let's go back to red. Let's use a way to express the right-hand sum for just n rectangles using the right-hand endpoints. So let's see if we could do that generically, because that's what we're going to have to do in order to let n go to infinity. We have to say, okay, instead of 4 rectangles, how could I do this for just n rectangles? So let's end by writing a generic sum for this. So if I want to write, so again, now we're looking at it from 0, we're looking at 0 to 1, but this time we're going to divide up into n subintervals. I'm not going to say the number, I'm just going to say n. So that the width of each one is actually going to be this idea of delta x, which is going to be 1 minus 0 divided by n. So it's actually just going to be 1 over n. So the first interval from here to here, this width is 1 over n. So this first endpoint right here is just 1 over n. And then I add another 1 over n. And so this next endpoint is going to be 2 over n, because we're going from 0 and we add 1 over n, and then the next one we add another 1 over n, so we get to 2 over n. And I'm going to actually move 1 out here just a little bit. And then we have 3 over n, and then we have 4 over n, and dot, 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 dot. And we get to some point like right here where we would call it just I over n. And then eventually we get over to 1. Okay? Because we actually add n of them up. And so the reason we get to 1 is because the last one, I, is actually n. So this, notice, would be n over n, which is, of course, 1. Okay, so that's our width. Our width is 1 over n. Each subinterval is going to be, we'll call it x sub I minus 1 and x sub I. So it's actually going to be equal to, based on the way we've done it, I minus 1 over n and I over n. Okay, so each subinterval, or we could say the ith subinterval, be specific. When we're at the ith subinterval, it's going to be x sub I minus 1, x sub I, and that's in the terms of this particular function from 0 to 1 that we're looking at, that's going to be I minus 1 over n and I over n. Now remember, we're going to use those right-hand endpoints to come up with our heights of each of our rectangles. So now to find the area, we're going to actually remember the function that we're looking at. I know it's off the screen right now, so I'm just going to write it again. So it's area from 0 to 1 of y under y equals x cubed. So to find the area, what we're going to do is we're going to take the sum of n rectangles. The area is going to be approximately, by the way. So the area under y equals x cubed on the interval from 0 to 1 is approximately equal to the sum of n rectangles. And when I say sum of those rectangles, I mean the areas of those rectangles. So how would we do that? How would we write that generically? So that would be approximately equal to, well, remember we're using the right-hand endpoints, and so notice up here, let's keep these up here. On the first interval, the right-hand endpoint is 1 over n. So, and the width of each interval is 1 over n. So remember that when we take area, it's width times height, or height times width. So the height of the rectangle is going to be the height of the function. So it's going to be, let's write f of. It's going to be f of 1 over n times 1 over n. That's the first rectangle. The next rectangle is going to be f of, we use the right-hand endpoint on the next interval, so it's going to be 2 over n times 1 over n. And then we keep going, and we go to the third rectangle. In the third rectangle, we're going to use the right-hand endpoint, which is 3 over n. I'm going up to the top of the screen here and looking at my interval, and that's going to be f of 3 over n times the width of each interval. And the width of each interval is uniform. It is 1 over n. And we're going to keep this going. We're going to add, we're going to get to the ith interval, so it would be f of I over n times 1 over n, and then we're going to keep going till we get to the n, and we're going to get f of 1 times 1 over n. And I will mention that we could write 1 as n over n if we wanted to. Okay, remember we've gotten to the nth interval, the last interval, and the reason we're at the endpoint is because that is n over n. It's how we set up the width of the intervals. So now that we have that, now we can actually plug it into the specific function, which was x cubed. So I'm going to go ahead and do that. I'm going to simplify this a little bit. Again, speed up the video because some of this computation stuff takes a little bit to get onto the screen. So we'll speed it up just a little bit. Okay, so let's come back and mention just quick simplification, plugging those into the x cubed and then simplifying. I noticed that there was in each of those terms a common factor of 1 over n to the 4th. I pulled that out and it left me with this nice little expression, technically this is 1 cubed plus 2 cubed plus 3 cubed plus I cubed plus all the way out to n cubed. And that can be expressed, going back to what we know about sums, we can even write this as 1 over n to the 4th, and we are going to use some summation notation in the next few sections. So this is 1 over n to the 4th times this entire thing. Rather than having to write that all out, which is kind of a long, right, that's a lot to write out, we can use our summation notation and say that that is the sum of I equals 1, we could index it, from 1 to n of I cubed. And if you need a little refresher on summation, do look that up. Look up summation notation, but that is exactly that. Okay, that is just a way to express that. You choose an index. I chose I for the generic ith term. It's why I actually carried that I throughout. You've got that generic ith term, and we are indexing it. We're adding up the terms I cubed from I running from 1 to n. And so this is our area under y equals x cubed on 0 to 1. This is how we can actually express it. And this is an approximation. Now here's what becomes pretty fun, where we're getting into our next branch of calculus, finding areas under curves. This is an approximation. Everything we've been doing, because we've used n rectangles. We can let n be 1,000 or 1,000,000 or 1,000,000,000 or, however many we want, but it is still an approximation. Okay, as long as we have a finite number of rectangles, this is still an approximation. But what we can do is we can take the limit. So this is exciting because now what we can do is we can say, you know what, the area is actually equal. Look, change from approximation to an equals if we throw a limit on that. What if we let the limit of those number of rectangles go to infinity of 1 over n to the fourth times the summation from I equals 1 to infinity of I cubed? Now we can say that it is equal to. The area is actually equal, the area, this exact area under y equals x cubed on 0 to 1, is actually equal to, if we throw in that limit, and that's kind of the important piece, if we throw in that limit, this becomes an equality rather than an approximation. And that's where we're headed. We're headed to allowing these limits to go to infinity, and then we can get the exact value of that area under the curve. So that's where we're headed. This was a little bit of a preview, but we got to know how to set these up. And so that's what we're going to practice in this section. We're going to practice estimating with left and right hand endpoints, and then we're going to practice setting up. How would we do it if we wanted it to be a generic n? And then we're going to get into, in the next section, how do we actually compute that limit?